Have you ever watched a robot arm move with incredible precision, or perhaps seen one snap into position with surprising speed, and wondered what invisible rules govern its motion? It turns out there are fundamental physical principles that dictate just how fast a robot can genuinely operate, completely separate from its motors or power. Kinematic constraints limit robot speed by defining the absolute boundaries of a robot's possible joint positions and velocities, as well as the resultant velocity of its end effector, based purely on its geometric structure and mechanical design. These limits exist regardless of how powerful the robot's motors are, essentially setting a speed limit based on how its body is built. At its core, kinematics is the study of motion without considering the forces that cause that motion. For a robot, this means understanding the relationships between its joint angles, velocities, and accelerations, and how these translate to the position and velocity of its end effector in space. Key kinematic constraints include joint angle limits, which define the maximum and minimum rotation for each joint, and joint velocity limits, which specify the maximum rotational speed each joint can achieve before it experiences physical damage or instability. These joint-level constraints then propagate through the robot's entire structure, directly influencing the reachable speed of its gripper or tool. To manage these constraints effectively, engineers typically employ several strategies in robot design and control. One common approach is careful trajectory planning, where the robot's path is designed not only to avoid obstacles but also to ranges within the safe operating speeds of all its joints simultaneously. Another strategy involves sophisticated inverse kinematic algorithms that can calculate the necessary joint velocities to achieve a desired end effector speed, while also checking if those joint velocities exceed their maximum allowed values. When a desired end effector speed would requiring a joint to move too fast, the system must either slow down or replan the motion. A fascinating insight from robot kinematics is the concept of a velocity ellipsoid, which visualizes the range of end effector velocities a robot can achieve at a specific configuration without violating any joint velocity limits. As the robot moves, this ellipsoid changes shape and orientation, highlighting how its manipulability and achievable speed vary across its workspace. Understanding these kinematic boundaries is crucial, as attempting to command a robot beyond these limits can lead to control errors, unexpected jerky movements, or even mechanical failure, rather than simply moving faster. Ultimately, recognizing and designing within these inherent kinematic speed limits is paramount for developing robust and efficient robotic systems. By carefully considering the geometry of a robot's joints and links during its design phase, and by implementing intelligent motion planning algorithms during operation, engineers can ensure that robots perform their tasks not only accurately but also at their optimal, safe, and physically possible speeds.
If you love robotics, like, subscribe, and keep building with us.